Welcome, everyone. Today, we're going to dive into a fascinating and pressing issue in the world of AI, the long-tail problem in large language models. Over the next few minutes, we'll explore the taxonomy, the underlying mechanisms, and the broader sociotechnical implications of knowledge scarcity in these systems. You've probably heard that simply making AI models bigger makes them better. But as this graph illustrates, scaling laws actually hide a critical failure mode. While scaling improves performance for the head of the distribution, which consists of high-frequency, highly reliable data like English syntax, viral pop culture, or Wikipedia headers, performance degrades non-linearly when we hit the tail. The tail is full of fragile, low-frequency information such as low-resource languages like Amharic, local statutes, rare diseases, and indigenous history. The core insight here is that learning rare facts requires a disproportionately larger volume of data, and unfortunately, our average case metrics completely mask these failures. So, how do we formally define this? Long-tail knowledge, or LTK, encompasses a broad class of low-frequency information. This includes rare entities, niche domain expertise, and historical facts that have limited digital presence. When models try to generate text from this area, they enter what we call the hallucination nexus. Because the signal-to-noise ratio is so weak, failures here manifest as perfectly fluent, yet entirely factually incorrect statements. This data sparsity isn't random, it actually manifests across four distinct dimensions. First is the linguistic and dialectical dimension, where tokenization fragments rare words in low-resource languages or dialects, like African American Vernacular English. Second is cultural and geopolitical. There's a heavy global north bias where Western concepts are easily recalled, while sub-Saharan or indigenous events are often hallucinated. Third is the specialized and domain dimension, which highlights the gap between general reasoning and specific facts, causing models to fail at predicting rare diseases or hallucinate local laws. Finally, we have the temporal and dynamic dimension, which includes both the new tail of post-cutoff events and the forgotten past of digitally sparse history. The loss of this knowledge doesn't happen at just one stage, it's a compound failure that cascades across the entire model lifecycle. It starts during pre-training with gradient dilution, moves into representation issues with tokenization and superposition, gets further penalized during alignment, and finally is restricted during inference. Essentially, if a rare fact somehow survives pre-training, it might still be crushed during alignment or filtered out completely during inference. Let's look at the math behind this. Optimization inherently biases against the rare in two ways. First is the signal problem, or gradient dilution. Loud signals from common facts literally drown out the quiet signals from rare facts, leaving tail features underlearned due to gradient starvation. Second is the storage problem, or superposition. While common concepts get their own distinct space, rare concepts are squeezed into noisy, polysemantic residual spaces. This leads to dangerous interference and overwriting of niche information. But the hurdles continue even after training. Step 3 in our cascade is the alignment tax from processes like RLHF. Models essentially learn to hedge or completely abstain from answering obscure, tail questions to avoid being penalized for hallucinating, which causes a phenomenon known as mode collapse. Then, in Step 4, probability truncation during inference, like top P or nucleus sampling, systematically lops off the low probability tail to ensure the text sounds coherent, directly silencing rare but correct answers. So, how do we fix this? We currently have a mitigation toolkit built on 3 pillars. First, we have data-centric approaches like importance weighting or generating synthetic data to flatten the curve. Second, we can change the capacity and architecture, utilizing mixture of experts or sparse parameters like the Mixtral model. Third, we rely on retrieval, or RAG, which allows the model to externalize its memory, telling it don't memorize, just look it up. However, there is no magic bullet, every single fix comes with a trade-off. RAG is fantastic for recently updated information, but it suffers from contextual retrieval failures and relies heavily on search index quality. Model editing tools like Rome or Mimit offer surgical fixes for specific errors, but they can cause ripple effects that damage related entities and degrade long-term coherence. Finally, human-in-the-loop systems offer high safety for critical fields like law and medicine, but they are completely unscalable because we simply lack enough experts to cover the vastness of the long tail. This brings us to a massive evaluation crisis. We are overly reliant on aggregate metrics like MMLU or Big Bench, but high average performance acts like the tip of an iceberg, masking deep failures underneath. We are suffering from hidden stratification, where a model might have a high overall score, but near 0% accuracy on niche topics, rare diseases, or local histories. This is the fallacy of AI functionality. High aggregate scores simply do not equal real-world reliability. Why does all this matter? The sociotechnical implications are profound. First, it affects epistemic visibility. Minority perspectives are statistically erased while dominant ideas are artificially boosted. Second, it creates unequal reliability, leading to high error rates specifically for non-English speakers and Global South contexts. Third, it introduces severe legal and medical risks due to the log-linear law of hallucination, where error rates spike as popularity decreases, but the AI's confidence remains dangerously high. Looking to the future, we face the existential threat of model collapse. As models are trained on web data that is already biased toward the head, they generate synthetic content that hallucinates the tail. The web fills up with this AI content, and future models train on it. This recursive training loop leads to a massive loss of variance and the permanent evaporation of low-frequency, rare knowledge from our digital ecosystems. To conclude, long-tail knowledge loss is a structural feature of learning from heavy-tailed distributions. We cannot simply scale it away. We must move beyond the average case paradigm. We need to adopt tail-aware evaluation, stopping our reliance on aggregate scores and stratifying performance by frequency. We need to build hybrid systems that shift the burden of rare knowledge from the model's parametric memory to governed retrieval systems. And finally, we must champion epistemic pluralism through the active curation of data to preserve the forgotten past and non-dominant perspectives. Thank you for watching.